Hey, let's talk about refraction and Snell's law. You ever looked at a glass of water and notice that the straw, when it enters the water, appears to bend? Like literally, look at this here. You can see at the boundary between the water and the air, the straw is going straight and then all of a sudden it looks like it bends. Well, it turns out that the light bends when it passes from the air into the water or the water into the air. And that's what we're going to explore today when we look at our notes on the refraction of light. So the refraction of light is simply the bending of light when it passes into a new translucent material. So the word refraction in this case means bending. So whenever you see the word refraction, just think the light is bending. And it's got to be a new, that's an important word, it's a new translucent material. Translucent means that the light can pass through it. So a brick wall is not translucent, so you won't see refraction of light through a solid object like a brick wall. What are some examples of where you might see refraction of light? So some examples might be if light passes from air into water, or vice versa, from water back into air. You're going to see some refraction. How about air into glass? And vice versa, glass into air. How about air into plastic? So if you're wearing contact lenses right now, the refraction of light from the air into the plastic and then the plastic back into the air is going to be responsible for this this bending of the light to focus the light better for your retina. Same thing for me wearing my glasses right now. Air into glass, glass into air is responsible for the bending of light to make my glasses help me see better. So we're going to take a look at our very first pattern in the bending of light. We start out with a diagram. And in our diagram, we're going to start out with the boundary. This is the boundary between two different surfaces. So this first material is going to be air. Okay, and then we're going to pick a second material. It's got to be different. Let's choose glass. So here's glass down here. When the light ray comes in, we draw it as a straight line. Okay, so the light ray comes in at a straight line, and it's going to strike this boundary at an angle. Okay, if it strikes it at an angle, we got to say an angle relative to what? And the what is called the normal. The normal is a dotted line. It's perpendicular to the surface, and we always label it the normal. Okay? When you have this normal, you always look at that first angle. This first angle is called theta I. You might remember the theta I is the angle of incidence. It's also, for the purpose of Snell's law, called theta 1. Okay? It's the incident angle, it's the incoming angle, it's also theta 1. Now, we're going to prove coming up that when light travels from air into glass, it's going to bend toward the normal, okay? So instead of going in this straight line here that you would expect if we had a ruler, let's say, this is the direction that we would expect for the light ray down like this. Instead, it's going to bend toward the normal like this. And we're going to show that coming up. Let's call this angle over here theta r, that's the refracted angle, and it's also called theta 2 for the purposes of Snell's law. Okay, so this is the diagram that we're going to work with here, and one thing I want to show you is that these two angles are related, and in particular, I want to suggest to you that the bending of light, the refraction of light, is dependent on two factors. Okay, the bending, the refraction of light is determined by two factors. The first one is the angle of incidence, theta I, so that's this angle up here. That will determine how much the light bends. And second, the types of materials. So in this case, air into glass, that's going to have a different impact than air into water, let's say. We're going to see that coming up. Okay? So key pattern number one, the very first pattern that we want to look at here is going to suggest this. If we look at the simulation again, and we see that as we change this angle, if we make the angle of incidence bigger, so this angle with respect to the vertical, with respect to the normal, is getting bigger. Notice that the refracted angle down here is also getting bigger. Likewise, if I reduce the angle of incidence, the refracted angle also reduces. So what we're going to do is we're going to express that in terms of key pattern number one. As theta I goes up, we expect the refracted angle, theta r, to also go up. Likewise, as theta I goes down, we expect the refracted angle, theta r, to also go down. Okay? So Snell's law is going to capture this pattern for us. All right? Excellent. Let's move ahead, and what we want to do now is talk about this second factor, the type of material. How does the type of material impact the bending of the light? Well, We answer that question by stating that the ability of a translucent material, so what it could be glass, it could be plastic, could be water, the ability of a translucent material to refract light, to bend light, is measured by the material's index of refraction, N. Okay, so we're going to take a couple of minutes now and really explore what is N, what does it mean, how do we measure it. Okay, but first I want to give you some examples of what some different N's are. So for a vacuum, remember a vacuum is just empty space. For a vacuum, N is defined to be 1. That's just what it is. Okay, what about for air? For air, the index of refraction is 1.0003. Okay, so very close to air. So light travels very similarly in air as it does in a vacuum. I should say very close to a vacuum. What about in water? The index of refraction is about 1.33, and it changes obviously depending on what solutes you have in the water. So 1.33, and then for glass, it's about N equals 1.52. And notice that we're getting denser as we go down. A vacuum has no density, air has a little bit of density, water has more density, glass has more density. Now, what I want to suggest to you is that we can now start to unpack what N is. And to answer the question of what N is, we have to state the following. We have to state that light slows down in all translucent materials. So when light passes, for example, from air into water, it's going to slow down. Or from air into glass, it slows down. Let me give you some examples. In a vacuum, we know the speed of light, C, is 3.00 times 10 to the 8th meter per second. In water, light travels still very fast, 2.26 times 10 to the 8th meter per second, but not quite as fast as it did in a vacuum. Likewise for glass. Glass is more dense. The light will travel at a little bit slower pace, 1.97 times 10 to the 8th meters per second. Now, it turns out that the index of refraction is directly related to the speed of light in that material. Okay? In fact, N, the index of refraction, is the factor by which the light slows down in a material. So if I go back to these indices of refraction that I want to show you here, if you compare these indices of refraction, notice that as the index of refraction got bigger, oops, I ran out of space here. As the index of refraction got bigger, going from a vacuum into air, into water, into glass, as the index of refraction got bigger, the speed of the light in that material got smaller. So a denser material with a bigger index of refraction had a slower speed of light, right? That's very interesting. So that's really what N is, okay? So what N is, we can really unpack this now. N is, and I think I wrote it here, we just unpacked it. N is the factor by which light slows down in a material. So we can express that in terms of this equation. We can say V, where V is the speed of the light wave in a material, which is, like we showed, not the same as the speed of light in a vacuum. The speed of light in a vacuum is C, okay? But if you take the speed of light in a vacuum and divide it by the index of refraction N, that will give you the speed of light in the material, okay? So once again, we see that inverse relationship. We can see that as these indices of refraction got bigger, the speed of light got smaller, okay? And you can see that as the index of refraction got bigger, the speed of light got smaller, and you see that inverse relationship in this equation. As N gets bigger, the speed of light in the material gets smaller, okay? That's the relationship between the index of refraction and the speed of light in that material. Now, another pattern that we want to explore is that as N gets bigger, as we said, V gets smaller. That's the inverse relationship. And one thing that I want to try to prove to you using Snell's law is the following. This is key pattern number 2. The more different the ends are, the more the light bends. Okay? If light passes from one material into the exact same material, it's not going to bend. We need those indexes of refraction, or the indices of refraction, to be different in order for the light to bend. So, for example, if we go back to our simulation, if I go air into air here, okay, this is air into air, there's absolutely no bending at all. Or if I go water into water, there's absolutely no bending at all. Or glass into glass, there's absolutely no bending at all. But if I go air into glass, you can see some of that light bounces off and it reflects according to the law of reflection at the same angle, right? But some of it passes through the barrier, through the boundary, into the material and it bends, okay? So these indices of refraction have to be different. So going air into glass will have a bending, just like air into water will have a bending as well. All right, very good. So the next thing that we want to do is we want to explore a little bit further these patterns. And we want to summarize these patterns by expressing, finally, Snell's law. And Snell's law is going to encapsulate these two patterns. We start with the diagram, the same diagram again. So we have the boundary between the two surfaces. Here we have air. Here we're going to have, let's say, glass. And we're going to label the index of refraction. So for the air, we're going to say, okay, the index of refraction of air is equal to 1. And the index of refraction of, you can say 1.00, that's fine. And for glass, n is equal to 1.52, right? So if we have a light ray passing through, so here's a light ray passing, it hits the barrier, it's going to find the normal. Here's the normal represented by this dotted line. Here's theta 1, the first angle, the incident angle. And coming into the glass, we're going to bend toward the normal, as we'll see coming up. And this is going to be the angle theta 2. All right, so here we go. This is the setup for Snell's law. So we call the first index of refraction N1 and the second index of refraction N2. And Snell's law states that if you take the product of the first index of refraction times the sine of that first angle, this angle right here, that's going to equal the product of N2, the second index of refraction, times the sine of theta 2. And this right here is Snell's law. Okay? And over time, we're going to see how those two patterns that we talked about are baked into Snell's law. Okay? So let's go ahead and do a quick example. So in our example, we're going to say let theta 1 be, we're going to make this 50 degrees. That's about to scale to this diagram. Let theta 1 be 50 degrees. And I can see that I ran out of room, so I'm going to say let theta 1 equal 50 degrees. We want to find theta 2. That's the angle of refraction. All right, very good. So now, let's just set up Snell's law. I'd like to solve it algebraically, if we can. So we're going to solve this for theta 2. So let's start out by writing out N1 sine theta 1 equals N2 sine theta 2. So to solve for theta 2, we have to get rid of the N2. So divide both sides by N2. All right. And then we have to get rid of the sine function. We all know that the opposite of the sine function is sine inverse. So take sine inverse of both sides. And that's going to give you theta 2 by itself. So we can just write theta 2 equals sine inverse of this expression, N1 sine theta 1 divided by N2. And you can see here that the ratio of N1 to N2 is really going to determine this this theta 2. And so the bigger this ratio is, or the more different N1 and N2 are, the more of an impact it's going to have on theta 2. All right, so based on the givens that we have N1 is 1, we have N2 is 1.52, and we have theta 1, we can plug all of these values into our equation, and we can get a number for theta 2. So this gives us sine inverse of N1 is 1, so that's 1 times sine of 50 degrees, divided by N2 is 1.52, and if you plug this into your calculator, you will get 30.3 degrees. So if we label our diagram now, theta 1 we said was 50 degrees, right? 50 degrees, there it is. And then theta 2 we just found was 30.3 degrees. You see how we argued that the light ray was going to bend toward the normal? We knew that this angle theta 2 was going to be less than the incident angle because this index of refraction, the second one, was bigger than the first one. N2 was bigger than N1. Okay? So we knew that it was going to bend toward the normal, and you can see that 30.3 degrees is in fact less than 50 degrees, so that checks out. All right, fantastic. So we were able to solve that problem, no problem whatsoever. And now I want to take a look at key pattern number 3. Okay? Key pattern number 3 states that if light passes from a low index of refraction, that's a less dense material, into a high index of refraction, that's a more dense material, the light bends toward the normal. Okay, and we just saw that, right? And if we go back to our simulation real quick, you can see going from air into, in this case, water, the light bends toward the normal. All right, good deal. We're going to come back to this, this second half of pattern number 3 in a moment. But first, what we want to do is we want to continue our example. So let's say that we pick up where we left off, right? So we found that if you have a boundary, and I'm going to ask you to draw a really important diagram here, okay? So you're going to need a big portion of your page to draw this. Let's start out with our first boundary. This is going to be air into glass. And then let's draw our second boundary. This is going to be glass. We're going to go back into air. Okay? So we go from air into glass and then back into air. Okay? This is like light traveling into a window, right? Two parallel boundaries. One from air into glass and then glass back into air. So let's start out by drawing the light ray coming in. So here is our theta 1, and we said that this was 50 degrees, right? So here's our normal. We said this was 50 degrees. And we calculated what the refracted angle was going to be. We said that this refracted angle down here was going to be 30.3 degrees. Okay? And now the question is, find the exit angle. When the question says find the exit angle, they mean find the angle that the light ray leaves the material. So the light ray goes into the glass, but now it's going to leave the glass. And the question is, what is the light ray going to do? Well, let's start by drawing our normal. Now, we need to predict what the light's going to do. Is it going to bend toward the normal? Is it going to bend away from the normal? Is it going to continue straight? Let's investigate. Now, the first question we have to ask is, what is this angle over here going to be? If this boundary is parallel to this boundary, see if you can use a little bit of geometry here. If you know that this angle is 30.3 degrees, then what would this angle over here be? You can see why this is called geometrical optics. So we're going to apply a principle from geometry called alternate interior angles, right? If this normal is parallel to this normal, because this boundary is parallel to that boundary, then we have two parallel lines crossed by a transversal, which means that this angle over here is going to be the alternate interior angle to 30.3 degrees. So this is also going to be 30.3 degrees. Now notice, this only works if we have parallel boundaries. Okay? So the question is, what's the light ray going to do? How do we solve this? Let's call this angle up here, let's call it theta 3. Okay? Let's call this theta 3 is 30.3 degrees. We want to find theta 4. Let's find theta 4. Now, the air up here has an index of refraction of n equal 1. The glass here has an index of refraction of 1.52, but then it's going to pass back into air where the index of refraction is 1.0 again, 1.0, right? So now what we're going to do is we're going to set up Snell's law, but we're going to do it in terms of theta 3 and this index of refraction here. So we might say, okay, the index of refraction of glass, so, you know, I'm going to write this equation again, so we're going to say the index of refraction of glass, so we're going to say n glass, or you could simply say, you know, n2 times sine of theta 3, right, is going to be equal to, now we're passing back into the air, so this is back to n1, where this is n2, passing back into the air here, so n1 sine, and this angle we're going to call theta 4. So we're applying the same law, Snell's law, where n2 is the glass here, theta 3 is the angle associated with this first material. Okay, we're calling it theta 3 because when we get to more advanced problems we have to start using this notation, so we might as well get used to it now. So this is going to pass back into air, so that's n1, and that's going to get us sine of theta 4. Okay, so now let's solve for theta 4. So let's plug in our numbers here. We're going to have n2 is 1.52, sine of theta 3 is 30.3 degrees, equals n1 is 1 times the sine of theta 4. Alright, so the 1 is going to cancel itself out, so we get theta 4 is equal to the sine inverse of 1.52 sine 30.3 degrees, or theta 4, oh my gosh, do you believe it? Exactly 50 degrees. So it bends in such a way that it matches the angle that it first came in at. It came in at 50 degrees up here, didn't it? And when it passed through back into the air, it was also 50 degrees. What does that mean? This only works if the two boundaries are parallel. If you look through a glass window at an angle, do you see a distortion of the image? No, you just see whatever's behind the window. And that's because the light rays don't really bend. Now there's a little bit of maybe a translation of the light ray, but you don't see a bending of the image. The image retains its normal shape. So that's very interesting. Now, this allows us to go back to key pattern number 3. So if we go back to key pattern number 3, it says if light passes from low end to high end, the light bends toward the normal. But now we had high end, this glass, into the air, and we found that it bent away from the normal. So we're going to say if light passes from a high end to a low end, the light bends away from the normal. Okay, very interesting. We see this confirmed also if we go back to our simulation. So if we make the first material the dense material, and we make the second material the less dense material, you can see going from glass into air here, the light bends away from the normal, not toward the normal, but away from the normal. And you can still see that some of that light ray is reflected back into the material itself. All right, good deal. Fantastic. This is wonderful. There is one more topic for us to explore. And this topic is called total internal reflection. I want to show you something kind of interesting. When light passes from a dense, so that would be a high index of refraction, a high N material, into a less dense material, that would be a low N material, there is a critical angle, theta C, critical angle theta C, at which all light reflects. All light reflects back into the material. Let me illustrate this for you using the simulation. So take a look over here. If we go from a dense material into a less dense material, so you can see this upper material is dense, and then there's a less dense material down here. Notice that yes, some of the light is reflecting back, but if we increase this angle enough, eventually the refracted ray, the bent ray, is passing parallel to the boundary at 90 degrees. But beyond that, notice that all of the light is now reflected back into the first material. There's no refraction into the new material. So there's some critical angle right there, that's the critical angle right there, at which no light passes into the new material. All of it reflects back. So once again, if we start at 0 degrees, and notice, parallel to the normal, there's no bending at all. Only when you start to increase that angle do you see any bending at all. But there is a point where it refracts parallel to the boundary, and then all of it reflects inside. And that is called total internal reflection. So let's take a look at this, and let's call this key pattern number 4. If, these are the two conditions, if A, light passes from a less dense, or from a dense material, that's a high N material. So if light passes from a dense material, a high N material, into a less dense material, a low N material, and if theta I exceeds the critical angle, then we have total internal reflection. Now, question is, how do you find the critical angle? Well, let's use a diagram. The critical angle is reached when, if you have a certain index of refraction, we'll call this N1, and this is the second index of refraction, N2, and we have some theta, call this a theta 1, we have some theta 1 at which the light is going to bend parallel to the boundary. So here is the light bending parallel to the boundary. So this, relative to the normal, would be 90 degrees. Okay? So a 90 degree angle would be our theta 2. This is the critical angle. So just to illustrate it again with the simulation, notice that we have some of the light refracting through, but once that angle gets to 90 degrees, the refracted angle, that's when we have total internal reflection. So we're going to find the angle where we're going to achieve a 90 degree refracted angle. Okay? So when we set up Snell's law here, we're going to say, okay, the N1 times the sine of theta 1 is going to equal N2 times the sine of theta 2. And what we're going to do is we're going to say, okay, this theta 1, this is now going to be our critical angle. This is going to be theta C. This is equal to our critical angle. Okay? And then this theta 2 is going to be 90 degrees. Okay? So if we now solve this for our critical angle, we're going to have the equation N1 sine theta C equals N2 times the sine of 90. Now we know the sine of 90 degrees happens to be equal to 1. So this term is going to cancel out. So now, if we solve this for theta c, we're going to get sine of theta c equals n2 over n1. And that allows us to solve for theta c. We get theta c is equal to the sine inverse of n2 over n1. All right, and there it is. That's how you calculate the critical angle. At any angle above the critical angle, all of the light is going to reflect back into the original material, and we will have total internal reflection. All right, that completes our notes on Snell's law and refraction. Thanks for watching.